Hello and welcome to this tutorial on Linpro. In this video we're going to demonstrate the main features of Linpro and how it may be used to solve elementary problems in structural analysis. We'll show you how to obtain the reactions, the internal forces and moment diagrams, as well as the total deflections of the structure. The first problem we're going to solve is a simply supported beam, which you can see is supported by a pin and a roller. It also has a distributed load, point load, and a point moment by the end. The section properties will be the default settings from Linpro, and we're looking for the shear and moment diagrams of the structure. Here we can see the main window of Linpro, as well as the grid we're going to be operating in. On the left, we can see the options to create joints, members, move joints, and define the grid of the working area. On the top, we have the options to create sections, determine the coordinates of the joints and the supports, create members, and assign the loads on every joint and member. All the icons that are shown here can also be found on the tabs above. The first job that we have to do is to select the units for our problem. We can do that by selecting the units icon on the bottom left and selecting the appropriate units for the occasion. In our case, kilonewton meters is the best option. The next step is to define the dimensions of the grid. To do that, we select the option on the left. Here we can input 20 into system width. We can keep the same height. We can keep the grid spacing to 1 meter per joint. Then we can input the joints directly into the working area by selecting the option on the left, or we can input the coordinates of the joint by selecting the option on the top, where we're gonna put 4 plus 8 will be 12 and 5, and for the last joint it would be 15 and 5. We can see now that the joints have been created. From the same window, we can also assign support conditions on each joint. In our case, joint 0 would be a pin, so Rx and Ry would be constrained. And also on joint 1, Ry would be constrained since it's a roller. Joint 2 would be free to move in every direction. We can now proceed to create the members of the structure. We can simply use the option on the left and create the members directly from joint to joint. To unselect the option to create members, we have to select the pointer on the top and then hit escape to renew the graphics. Now that we have created our members, we can also define the cross sections we can assign to each member. We can select the option on the top, where we can see the default section that Linpro creates automatically. We can also see that the modulus of elasticity is the one we want, and we can change the cross-sectional area to 4. We click change, and now the changes have been applied to the type 1 cross-section. Now that we have completed our structure, the next step is to assign the loads. We can do this by selecting the icon on the top, and here we can see the different types of loading we can assign to the structure. In our case, we only have point loads and distributed loads. For the distributed load, we're going to use P1 to be minus 40, P2 to be minus 40. We'll set the distance on the member to be relative. You can use 0 and 1. Then we click define, and here now we have created a distributed type of loading. We will assign it on member 0. You can also see the load that has been assigned to the member. The next loading we have to create will be the point load, which will be minus 20, and we'll name it point load. We will click define. This we have to delete. Now we have created our point load, we can assign it on node 2, which we'll do here. Finally, we'll create our point moment. Which will be minus 150. We'll click define, and then we select node 2 again and click assign. You can see that the positive sign accounts for counterclockwise orientation. Click OK, and now we have assigned all the loads. Our structure is now ready for analysis. We can click the green icon on the top, and here we can see the deflections along the structure. We can also click to see the reactions of the supports, and we can also see the moment diagram, the shear force diagram, and the axial force diagram, in which case there is nothing to be accounted for. We can also change the dimensions of the diagrams to clearly see the differences between them. And this concludes the analysis of problem 1. Let's move on now to problem 2. This problem also contains one vertical element along with the horizontal element. Point A is supported by a roller, point B is fixed connected, and point C is a pin. In this case, we want to determine the axial, the shear, and the moment diagrams along the structure. This problem can also be solved in a similar fashion as to the first problem. First we validate that the units are the ones we want. Then we can proceed with changing the grid. This grid is appropriate for this case. Therefore, we can proceed in defining the joints. Here we can select this joint, then we will move 1, 2, 3, 4, then 1, 2, 3, 4. Having established the joints of the structure, we can now assign support conditions. We can change the support conditions from the top option, and on joint 0 we have a roller, and on joint C we have a pin. We can now proceed to assign the members of the structure. We can select the icon on the left, then select the joints to create the members. Then we deselect and renew the graphics. The next step is to define the cross-section properties. We select the icon on the top, and then you can see that we have the same modulus of elasticity, and we change the cross-sectional area to 4, hit change, and now have established our cross-section. The next step is to assign the loads. We go to the loads icon. In this case we have only point loads. In this case we want, for member 0, we want a load of 6 kilonewtons facing down at a relative distance of 0.5. We define it. You can assign it to member 0 to validate that it's correct. Then we begin to define the load for member 1. Yes, we name it member 1. We erase the previous value. Here we write -2 in the x direction. The relative distance is the same. We define, select member 1, and assign. And now we have established the load pattern for the structure. We can now proceed to the analysis. We hit the same green icon. We can now see the deflections. We can see that the vertical element has moved to the left. We can also see the reactions, as well as the moment diagram. the shear force diagram, and the axial force diagram. Here, the moment diagram, we can increase the dimension of the diagram so we can see properly what are the values and the shape of the diagrams. This concludes the solution of problem 2. The next problem is a little bit more elaborate. We can see we have a frame structure supported with 2 pins on points A and D. Point C is fixed connected and point B is a pin. We have distributed load on the inclined element and 2 point loads on the horizontal element. In this problem, we are following the same pattern. First, we validate our units are correct. Then we proceed to define the grid. In this case, we can assign a system width of 20. The next step is to define the joints. Select the joint icon on the left. Select this point. Then we move by 3, 1, 2, 3, 1, 2, 3, 4. Then we begin by moving by 6, 1, 2, 3, 4, 5, 6. And we go down by 4, 1, 2, 3, 4. Our joints are ready. Now I can proceed to assign support conditions. Joint 0 will be a pin, as well as joint 3. And that concludes the support conditions. Next, we'll have to assign the members. Select the members icon. Then we connect all the joints together. We deselect and renew. We validate that the section properties are the ones we want. This is the same, and 4 change and hit OK. Now in this case, although we have 2 pins as support conditions, we have an internal hinge in the structure. This we have to define in a different way. We go to the members icon. Here we can see the members and the joints they're connected to, as well as the section name they're assigned to. Now for every internal hinge, at least one member should have a constraint in the moments. All other members have to have the moment released. In this case, we have 2 members on joint 1, members 0 and 1. So we select member 0, hit end releases, and then we click joint 1. You will see that the joint has turned gray. This means that the joint has now become a hinge. If we also remove the moment support from member 1, we will see how this changes. Now this shows that the structure is unstable. This means that joint 1 is restrained by neither of the members, and this situation is unstable. Therefore, we have to keep one element with moments supported. And now we have created an internal hinge. The next step is the assignment of the loads. Hit the load icon, and now we have distributed load on the inclined element 0. This load would be a value of -3 and -3. However, since this element is inclined, we're not going to be using the global y-axis, but we're going to use the local y-axis. To help you understand this better, you can use the hint button. Here you can see how the load is assigned in the local y-axis. If I had changed to global, then the load will be vertical on the global axis. We also want the relative distance to be 0 and 1. We define, and then we assign the load to member 0. The next step is the assignment of the point loads. The point loads are located at 1/3 and 2/3 of element 1. Therefore, we're gonna name them point left. We're gonna assign a value of -8. And we're gonna need a relative distance of 0.33. Could also use an absolute distance of 2. But it will be the same scenario. We define it. We assign it on member 1. We can now define the last load. Be point right. Will be at a relative distance 6.7. The value is the same. We define it. Then we assign it to member 1. Okay. Now have established the loads. All that remains is to run the analysis. Click the green icon. You can see the deflections. You can see that the section has moved to the right. These are the reactions. These are the moments. We can now clearly see the moment pattern on member 1. You can see that it's 3 segmented lines, whereas on member 0 we have a curved line. You can see the shear force diagram. You can see it more clearly. You have the axial force diagram. That concludes the analysis of problem 3. The last problem is a truss element problem. This structure is made of truss elements and is supported by a pin and a roller, and it has point loads on the top joints. We want to determine the axial force diagram of the structure. We will see how truss elements are defined in a similar fashion as the internal hinges are defined in the previous problem. First, we follow the same pattern. We ensure that our units are correct. The grid is appropriate for this occasion. And now we can proceed to define the joints. Select from the left, this is joint 0, and then we go 1, 2, 3, 1, 2, 3, 1, 2, 3, 3, and 3. We know that joints 0 and 2 are a pin and a roller. We have determined our joints. The next step is to determine the members. Select the members icon and we connect all the joints. Now to not start from joint 2, we'll have to deselect, hit escape, and reselect the members icon to continue drawing the members. Again, deselect, then select the last one, and these are the elements. Now please note that the direction of the member assignment will determine which side is positive and which side is negative. By default, the first point will be the start and the last point will be the end. And of those points, the bottom and right side will be the positive, and the top and left will be the negative. Then we have to validate that the cross-section properties are the ones we want. So in this case, modulus of elasticity is correct. We have to change cross-section area. Now that we have defined the members and the section, we have to transform these elements into truss elements. So far, the program only knows that it has regular members. To do this, we'll go to the member section. And similarly to creating an internal hinge, we'll release the moments in all the joints. In every joint, we'll keep one element with moment restraint. It does not matter which element keeps its moment, only that only one out of all elements in the joint retains the moment restrictions. Now we select first element, release the moment on 1 and 0. We can see now that the moments have been released on these two joints from the part of element 0. Go to the next member and we follow the same pattern. And we repeat that until only one element remains on every joint. Now we can see now that on joint 2 we have created an internal hinge. We proceed. Now our element 3. We've also created a hinge on joint 3. We release all joints. Alright. And we keep going. We've created 2 more hinges. Now we go to the inner elements. We cannot select joint 0 since we have already created a hinge, so we only select joint 4. Still have one more element to go here. We choose element 7. We release only joint 4. Now we have a hinge on joint 4. Similarly, we select the other 2 elements and release the moment on joint 1, and also release on joint 1, and there you have it. Now we have created a structure with truss elements. To make this structure understand that we have created truss elements, we need to release the moment on all joints. That is why the only force that can be developed in those elements is the axial force, which is exactly similar to the truss elements. The next step is to assign the loads. Go to the loads icon, go to point load, select, we'll name this 50 kilonewtons. Gonna write minus 50. We want it on node, so therefore we define it as it is. We also have 20, so we're gonna name this 20. We define it, and we also have 40. And it's 40. The absolute or relative distance does not matter since we'll be applying the loads on the joints. So we select node 5, we assign it, select node 4, and we assign it, select node 3, we also assign the load. Now we have assigned all the loads. The only thing that remains is to run the analysis. Hit the green icon. Here we can see the deflections. You can see the reactions. And now you can see that the moment diagrams and the shear force diagrams have no value. That's because truss elements cannot develop moment and shear. We can also validate if we have created the structure properly using truss elements when these two diagrams have no values. Here you have the axial force diagrams, and this is because there's not enough space. We can increase the size of the diagram to see them clearly. That concludes the analysis of problem 4.